So our last speaker is Tom Wilbanks, who's going to talk about enhancing resilience to climate-related surprises in coastal cities. Mr. Wilbanks is a corporate research fellow at the Oak Ridge National Laboratory. He conducts research on such issues as sustainable development, resilience as a goal for human and natural systems, and impacts of and responses to such global issues as climate change, which we all believe in, right?
There's nobody in this world that I love and respect more than Margaret Davidson, but everybody in my community hates to follow her on a program. She's so vivid in what she says and how she says it that everybody else looks like they're going from Technicolor to black and white. And with that apology, let me move ahead to say that what I propose to do with this last part of the last session in the meeting is to summarize why climate-related surprises are threats to systems that we care about, to summarize why cities are a particular concern, especially in coastal areas, and to sketch out some pathways that respond to a call of action, really following up on what Margaret has just had to say. Let me start with this diagram, which you've seen this morning, I think probably earlier in the week, which charts out the representative concentration pathways on the right. This is related to the fact that impacts of climate change are no longer hypothetical. They're already being observed, and some of them are already becoming serious. Meanwhile, greenhouse gas emissions are continuing to rise, making severe climate change more likely than moderate climate change. These 4 RCPs were actually defined back in 2007 at a meeting in the Netherlands to sort of lay out a range of possible futures for the world's climate, with a bottom limit, RCP 2.6 defined in terms of watts per square meter of radiative forcing, an upper range of 8.5, 2 intermediate pathways of 4.5 and 6. Back in 2007, the feeling was that the bottom limit, 2.6, was probably not achievable anymore, and only the Europeans believed in it. 4.5 was what we were aiming at as a realistic kind of future, which would be associated with a 3 or 4 degree centigrade temperature increase. 6 was just about equivalent to what we've considered in the past the worst kinds of scenarios we look at, like A2 and A1FI. 8.5 was just sort of up there to put a ridiculously high bound on it. But since 2007, if you look at those black dots in the lower left-hand part of the graph, those are the global greenhouse gas emissions that we're observing. And if you see what's happening, that's on a track that's slightly above the assumptions for RCP 8.5, which was inconceivably bad only 6 or 7 years ago. Now, for that reason, actually in the last 3 or 4 years, the attention to climate change impact assessment has shifted from being based on 4.5 to being based on 8.5. Because that looks like not only a possible future, but if we're not careful and not more successful with mitigation, a likely future. In the meantime, in the last several years, we've had an unusual series of climate-related extreme events. Severe storms such as Sandy, the Washington, D.C. community learned a new word called derecho. Droughts, floods, winter tornadoes, wildfires, and some of that's continuing this year, at least wildfires and droughts. The National Climate Assessment concludes that such extreme events are related to longer-term climate change. It's the first time the science community has said that in public. And this means that projecting extreme events over the next several decades, especially for critical infrastructures, has become a high national priority. This is the way that we've looked at climate change impacts traditionally. We identify certain kinds of risks, the 5 that are across the bottom. We associate them with different levels of average global warming, not because warming is the only issue, but those are sort of proxies for overall climate change. And the colors on the graph show how bad it is. You can associate that with concentration levels of greenhouse gases in the atmosphere. If you look at the climb of those boxes of where the greenhouse gas emissions are with different kinds of climate futures, the one that's next to the right, 720 to 1,000, RCP 6.0 assumes a concentration of 850 parts per million. It's solidly in that box, which means you're right against the area where nearly all of those columns are changing into deep red. RCP 8.5 assumes a concentration level in 2100 of 1,370 parts per million and rising. That's well above the right-hand box there. That puts us up in the range of very severe impacts associated with global temperature increases of 8 degrees centigrade or more. That's very serious indeed. Now, of course, climate change is not the only concern that coastal hazards management has to deal with. They're also concerned with threats such as public sector budget crises, especially limited resources for public sector infrastructure revitalization. Where do you come up with money when you got to keep your budget constant and not raise taxes? Industrial accidents, pandemics, economic downturns, and terrorism. Particular concerns include perfect storms, where several different threats happen at the same time. There's just one example which comes from the outskirts of the city of Charleston, South Carolina, during a community resilience exercise. Consider a county or a city council that can only enact emergency actions to respond to a storm if it has a quorum at a meeting, but a pandemic has too many of the members of the council sick to come to meet the size of the quorum. An even greater concern is if the return time for one or more threats is very short, so you have very little time to recover from the last one. So why are we so worried about becoming resilient? Well, there's some attitudes that we have to overcome. One attitude is we've coped okay in the past, so we can handle that in the future. In general, we haven't coped that very well in the past. That's a mistaken impression, but people have it. Another is that the future is unpredictable, so we can only be prepared to respond to events, not to reduce the impacts of unlikely events if they were to occur. We focus on responding, not reducing vulnerabilities. Another point of view is it's not my problem. My concern is what's happening now and in the near future, not with what might happen a decade or more or half a century or more from now. Still another, it's not my problem, because if things get bad, the government will take care of us. That's a particular problem if the government people are thinking about the attitude just right above it. It's not on my watch, I'll be out of office before it happens, so don't bother me now. And finally, the point of view that says science doesn't offer any help in anticipating and responding to climate-related surprises, especially in the near term. It's only concerned with gradual changes in the long term. So what good is it? Well, the fact is, if we look at the current very strong, even kind of compelling interest in extreme events over the next several decades, where are projections of those exposures coming from? Well, you can look at climate change scenarios. They project some variables of interest, mainly temperature and precipitation changes over the long term. But they don't help much with extreme events over the next several decades. In fact, most of their scenarios don't even begin to diverge for several decades. Other sources of projections of exposure to extreme weather events are of two types. One is events that are determined by climate variables that are not included in climate models, such as sea level rise and storms. The other is events that are determined partly by non-climate variables, such as floods, which depend partly on what's on the land surface, droughts, heat waves, and wildfires. For each of these categories of extreme events, there is scientific work going on. There are people doing research on how to project those kind of events. Here are some examples of people who are working on different categories of extreme events. They're all over the lot. Most of them are only indirectly connected with climate change scenarios, if at all. They use them a little bit for framing where things might go out in 2040 or 2050. They don't use them for the projections what would happen in the next several decades. And that's kind of a challenge. Let me give you an example of one kind of work that's going on. This is work that's been done by Carrie Emanuel here at MIT, which you know, of what is likely to happen with tropical cyclone projections over the next century or so, including by decades. And if you, one of the things, it's interesting that this not only projects increases in the intensity of cyclones, which you would expect because the sea surface temperature is rising, it also says that frequency will increase, when in the past that's been kind of a controversial question. Not only that, if you can see the dates for 2015 and 2025 in the middle of the graph, they show significant increases over what was happening in 85, 95, and 2005. This says in the next several decades we're likely to see an increase in frequency. Now, not everybody agrees with Carrie on this, but it's an example of useful scientific work that's going on. This is an example of one of the unfortunately, fairly small number of cases where the climate scenarios themselves are useful, because what the climate scenarios say is reinforced by observational evidence from the recent past. One of the most confident predictions of these climate models has been that a greater proportion of rainfall will fall in a small number of extreme rainfall events. It turns out that, that observations over the last several decades show that change already happening, and it has two implications. It says not only are risks of flooding increased because you have more of the kind of events that can cause flooding, but risk of droughts also increase because there are more days during the year when there's no rain falling. So it has implications that are pretty severe in several ways. Well, if we can project extreme events even as sort of shock scenarios to analyze, there are tools available to simulate the effects of these things. There's some models that are being used in 3 of the Department of Energy laboratories that use approaches that were originally developed by DHL, by DHS through their National Infrastructure Simulation Analysis Centers that are supposed to look specifically at the impacts of extreme events on infrastructures and other systems that we care about. They're focused on impacts at relatively local scale, cities and small regions. They include very detailed facility asset-specific geocoded databases on every power plant, every transmission line, every electricity distribution system, every oil refinery, every oil storage depot, and so on. And for the whole United States, they're explicitly concerned with interactions and interdependencies, not only among different infrastructures, but among components of infrastructures themselves. And the fact is that they were developed back in the years after 9/11 to simulate impacts of possible terrorist acts, but they've mainly been applied for decision support when something like Sandy or Irene hits. They go in to help responders understand what to expect in a few days. And then after that's been done, they go back and see where they got their models wrong and try to improve them. They're getting very accurate. This is the way they look at the infrastructures that are exposed to events as a system of systems. This kind of depicts how they try to connect individual components of each infrastructure with components of other infrastructures, so that you can say if the power goes out, electric light, the traffic lights go out, the traffic slows down, emissions increase, and so on. And that means that each of the infrastructures has to be represented in great detail in order to have that kind of capacity to connect components to components. And once you have that in place and you've debugged it through a lot of applications, you can apply it to simulating effects of a particular extreme event. Back in 2012, the emergency preparedness people in Florida developed a handful of hypothetical hurricanes and said, what would the effects be if these were to happen? This is based, each was named after a member of the office, and this is one that was named after a guy named Charlie in the office, a Category 4 hurricane that was hypothesized to have that kind of track. And these models made it possible to say, if that happens, then here are the electricity distribution substations that would be affected, and here are estimates of how long it would take to get the service back in place. That's just one example of a lot of kind of simulations that can be conducted using these tools. But in general, the science of projecting extreme weather events is not as mature or accessible as the science of projecting longer-term climate change. It's harder to find. It's developed by different agencies and different researchers using different approaches and assumptions. It's highly uneven in its treatment of estimates of probabilities and the time frames it uses, and that means it's very hard to put them together to look at multi-threat risk management and resilience enhancement strategies. This is a national need for data analysis that's starting to get considerable attention. You're familiar with the President's Climate Change Action Plan, which calls for a data initiative. It calls for a toolkit for climate resilience. We're hoping we get them to pay attention to things we need to add to what we have, not just loading in what we have right now. It's being followed up by a number of activities, including a high-level interagency council on climate resilience and preparedness, its working group on infrastructure resilience, an interagency task force on catastrophic risk modeling and analysis, a new NES-NRC roundtable on risk resilience and extreme events. I spent the week in Washington a few weeks ago going around talking to the alphabet soup of people there, OSTP, CEQ, USGCRP, NASNRC, and everywhere I went for that whole week, I heard three words. One was extreme events, a second was infrastructure, and a third was resilience. Those are things people are talking about, even if they're not fully sure what they're talking about. Well, let's look, sort of revisit climate change concerns for urban areas. I'll first talk about some urban areas in general and then give you one slide on particular concerns for coastal cities. We're concerned about cities because they're especially vulnerable for several reasons. One is that's where most of the people live. The projections are that net global population growth in this century will almost certainly be in urban areas. That means if the world population increases by 1 billion people, that's like adding 100 additional cities of 10 million people around the world, mostly in developing countries, and we can't manage the cities that are there now. Second is that these cities are there because for good reasons. People come into cities looking for job opportunities, for amenities, and so on. If the viability of an urban area is brought into question, all those services are at risk. Consider Detroit as an example in the United States right now. Climate change adds new kinds of threats through things like storms and sea level rise, also the possibility of heat waves, the possibility of wildfires in the West. There are thresholds regarding temperature changes that especially affect health indicators, although coastal cities are somewhat less exposed to that than interior cities because the temperature increase is moderated by the sea close to the coast. There are concerns about water resource connections. Cities need a lot of water. There is the fact that urban areas depend on systems for inflows and outflows, which themselves may be vulnerable. They depend on supply chains to bring things in. They depend on waste management and markets for things to send them out. And they compete with other cities for talent and capital investments in the context of an informatics revolution, things that affect perceived risk and uncertainties affect that. We care about urban areas because they're often located in especially vulnerable locations. Urban areas especially located in coastal areas and major river valleys. IPCC has estimated that a quarter of the world's population live in cities in these kinds of vulnerable areas. The fourth assessment report of IPCC used one case as the worst case vulnerability to climate change impacts in the world, and that was vulnerabilities of Asian megadeltas to a combination of storms and sea level rise. For example, Shanghai. Our experience in the U.S. with Katrina and Sandy adds to that. Urban areas are also important because so many of our vulnerable populations live there. The poor, the elderly, and very young, those already in poor health, the disabled, those living alone. It turned out in New Orleans after Katrina, the most vulnerable people in that city were elderly people living alone with pets because they couldn't get on the buses to evacuate if they took their pets and they wouldn't leave their pets. We don't understand these kinds of vulnerabilities well enough. You recall the story of the Paris heat wave in 2003, where a lot of the people who died were elderly parents of families who had gone to the Mediterranean for their summer vacation in August, leaving the parents behind in unair-conditioned spaces. There are also concerns about how climate change can add to pressures on local government infrastructures that are not doing very well already. They're often fragmented, often raise social equity concerns, as we've heard here today. Their response capacities are often undermined by social inequalities, dysfunctional social dynamics. They can't work together, they don't talk together. When we know that social dynamics are at the core of community resilience to threats and surprises, the ability to come together across boundaries between public and private sector and community groups to address problems. And as I mentioned, particularly severe limitation of public sector funding for capital investments to improve and revitalize infrastructures. People also tend to forget sometimes how important cities are beyond their own borders. They're important for climate change responses at regional and national scales because they are our financial centers, they're our industrial centers, they're our media centers, our innovation centers. They have most of the votes in a one-person, one-vote democratic decision-making system. And very often, the people at the regional, state, national level don't appreciate the value of cities enough to help support the maintenance of those kinds of services. Finally, a few things on coastal cities. Why are they especially sensitive and vulnerable? Well, the obvious is that they're exposed to coastal storms combined with the sea level rise. including flooding, of course, and especially in regions subject to land subsidence such as the Gulf Coast. They're also exposed to saltwater intrusions, but there's some other things that are also important. If we think about cities such as Seattle and San Francisco and New Orleans and Miami and Charleston and New York and Boston, and they're concerned with threats from coastal storms and sea level rise, what are the options? You can put up barriers like walls. You can harden facilities like Jim's example of the house on the Texas coast, or you can relocate. Now, as threats from climate change grow, threats of coastal impacts grow, it gets harder and harder to protect all the coastal cities with a combination of barriers and hardening, which raises additional pressures for relocation. But how in the world does a city take historic urban landscapes, not to mention people living in high-rise apartments who like to have a view of the water, and talk about relocating those kinds of things? It's a very serious kind of challenge that is distinct to coastal cities. We know about coastal economic sectors, ports, shipping, storage, also fishing, the importance of international linkages. Most of the coastal cities were built during the age of sea travel, and connections with the rest of the world or other regions are a part of how they work and how they see themselves. In many cases, coastal cities are located at the junction of a coast and a river, with harbor, with the further exposures to flooding from upstream precipitation and the importance of vulnerable bridges and tunnels. In relatively low-lying areas, there are problems with stormwater and wastewater drainage. There are often issues of sustainable water supply, either because they're dependent on interior reservoirs, which may be affected by climate change, or because they're dependent on well water, which is threatened by saline water intrusion. There are constraints on urban form. If half of your city is water, then the things you can do on land is limited to the other half of your periphery. For historical reasons, coastal cities are often somewhat older than cities in the interior, which developed later on, which means that the infrastructures are older and more subject to stress. Given the current challenges, how do we start thinking about resilience to surprises for cities and coastal areas? Well, there's some relevant concepts that are emerging. Jim mentioned the SREX report, whose full title is there on the screen, which focused on how adaptation to extreme events is different from adaptation to climate change more generally. Adapting to low probability, high consequence events. And it's associated with three growing concerns. One is an awareness that there are risks and losses and damages from climate change and extreme events that we can't any longer avoid. We have to figure out how to cope with that and to deal with the damages that result. The second is that there are limits to adaptation impacts, especially if climate change is severe rather than moderate. Some things we choose not to do because they're more expensive, some things that we just can't adapt to. And finally, the reality that if incremental adaptation cannot sustain systems that we value in the face of exposures to impacts, then those systems are going to have to consider transformational adaptation, much bigger changes in order to maintain their system services, not just after catastrophes, which we do all the time, but in anticipation of catastrophes in order to reduce risks and costs. And finally, there are some early experiments with integrated analyses, such as one by Entergy in the Gulf Coast region that I'll just touch on very briefly. Regarding these general points regarding loss and damages that cannot any longer be avoided, this is a point that the recent IPCC report made for the first time. It's the focus of a growing international loss and damage work program. For example, the islands of Kiribati and Tonga in the Pacific are buying land on Fiji Island to relocate their populations before the end of the century. It's related to an underlying theme that's just below the radar screen, especially internationally, which is that if you can attribute losses and damages to people who created them, then in some sense the victims ought to be able to sue for compensation. I can tell you the international fossil fuel industry is very concerned about that. It's being supported by significant analytical work, such as a recent World Bank report that looks at their experience with climate and disaster resilient development, mainly exposed to climate variability. and it focuses attention on capacity building for coping, financial support for recovery efforts, and compensation. Regarding limits to adaptation, this is a diagram that sort of shows frequency of impacts and intensity of adverse impacts, and says down in the lower left corner, those are acceptable risks. Up in the upper right hand, they're intolerable risks. Somewhere in the middle, there are things that are more judgment calls. This is such a simple concept that you say, duh. But the issue is important enough that it was published in the journal Nature Climate Change last year, because there's nothing else like it in the literature. Regarding transformational approaches to adaptation, well, as I said, sometimes if incremental adaptations are not enough to keep acceptable impacts within acceptable bounds, then more substantial adaptations are likely to be required. Things like significant changes in systems involving implementations at a much larger scale, or options that are truly new to a particular location or a system, or options that transform places and or shift locations. Big changes. As I said, some of these they're familiar after catastrophes, but hard to do ahead of time. There's some stuff in the literature about ways to do that. I mentioned something that Energy's done on the Gulf Coast. Their concern as a regional utility is that if the Gulf Coast is really vulnerable, the oil company and the chemical industry can pick up the stuff and go somewhere else. A regional utility can't do that. If their customer base is eroded by climate impact, they're out of business. So they put together a study to try to better understand how to make their region more resilient, not just their own utility. Included some economic analyses that I won't try to cover, working with Swiss Re. They looked at a range of adaptation options. This is a McKinsey curve that from right to left shows the options that are the greatest payoff per cost down to the lesser. Also, some of the over on the left are easier to implement. And they developed a 9-point plan for the region to keep its resilience at its current levels by 2030, that 2/3 of which would be paid for by the private sector, which they're out talking about to civic groups and so on in the region to try to encourage that kind of behavior to happen. Finally, I'm just going to wrap up by saying a few things about what pathways to greater resilience to surprises in cities, mentioning multi-hazard approaches, community engagement, what-if contingency planning, learning to imagine the unimaginable, increased flexibility, and expanded partnerships. Here's an example of multi-hazard planning. Cities such as Philadelphia have been very concerned about wastewater and stormwater management to reduce flooding. And they came up with something called the Green City Clean Waters Program. They brought together developers, community people, and government people and said, let's figure out how to do this together. And they came up with a plan where the city enacted building codes that requires new developments to incorporate elements that reduce impervious land in the city. And their analysis says that over 25 years, this will convert more than 1/3 of the city's impervious land cover to green facilities with no cost to the city government. And not only to that, the neighborhood involvement in this stimulated them to get more actively involved in city government, and they've set up a model neighborhood program to pursue that. One other quick example is an initiative by the American Society of Civil Engineers to explore changes in engineering codes and standards for new construction that would increase resilience to climate change impacts in a multi-hazard context. How might codes and standards pay attention to changes from historical conditions in the things that affect building resilience? For example, how do you do a building code and standard that encourages flexibility? It's a real challenge, but this is an example of something that's coming out of the expert community that does not require a congressional vote to implement. It's the sort of thing that we really need to applaud and encourage. Some other steps worth considering. Margaret mentioned communities of practice, and I'll say a bit more about the Gulf Coast and that. We need to encourage and support participative contingency planning, which she also mentioned, doing some what-if exercises, not as predictions to plan for, but as thought exercises to think about implications of what might be going on, to convert currently unimaginable things to things that are now imaginable, to talk about implications, perspectives, preferences, and issues. These exercises can be supported by the kind of tools I mentioned earlier that sort of visualize impacts. And we need to broaden user perspectives in climate and coastal management science and research priorities, looking for research agendas that are anchored in action needs, the term actionable science or use-inspired science. For example, more linkages with the NOAA RESAs. I mentioned the Gulf Coast community of practice as an example. There are other communities of practice around. This is one I just seem to know more about. This was catalyzed by local leadership, mainly from people supported by NOAA programs. It had seed funding from the NOAA National Sea Grant College Program to the NOAA Gulf of Mexico Regional Collaboration Team and the Gulf of Mexico Sea Grant Program, also supported by people from NOAA RESA programs such as well, there are a number of people in that we know from the RESA program that were important, like Lynn Carter, who's now off in Uganda doing other kinds of things. It was intended to establish a long-term community of practice involving, focused on extension, outreach, and educational professionals in the region, the fabric that connects the stakeholders with the science, to assure continuing dialogue and information exchange. And there's been very active participation in this, including webinars and annual meetings, to where it's really self-sustaining. People are finding value from this in getting to know each other and being better informed in providing their advice to the people they deal with. Thinking about responses tends to emphasize a need to rely less on historical practice and responses, more on robust risk-based adaptive decision frameworks, combining elements of both structural and non-structural approaches, in other words, both physical structure adaptations and management structure adaptations. Ideas on the table include more flexible, adaptable operating rules, better coordination between national, state, and local levels of risk management, improved partnerships with relevant stakeholders in assuring challenges and determining effective and equitable responses, and some focus on figuring out where backups and redundancies ought to be encouraged. Particular concern with inflexible laws and policies defined in terms of stationary historical baselines when that's not going to be relevant in the future. Okay, I'm finishing up with 2 summary slides, Mr. Moderator. And I think these kind of summarize the 3-day conference, not just this talk. Climate change is going to present challenges for coastal cities in the U.S., especially from climate-related extreme weather events combined with other stresses. If climate change turns out to be as severe as now appears to be most likely, some of these challenges are likely to be very severe. In coastal hazard management, the only surprise would be if there are no surprises. There's no such thing as not adapting. The challenge is to find adaptation pathways that avoid serious costs to systems, services, and or populations. There are very serious emerging reasons to consider the possibility that some U.S. coastal areas face threats in the next half century that could transform their landscapes and ways of life. We need to start considering contingency plans. Let me quote Margaret on this from a talk she gave in College Park last December. She said, "Mark my words, sea level rise of 3 to 5 feet in the next 30 years and the Gulf Coast is toast." Okay? That we need to be thinking about those kinds of possible futures to see what we need to start talking about now as solutions. And then there's a shortage of knowledge in many cases to underlie these discussions. So here's the last slide. At stake is the sustainability of many systems that we care about in the coastal areas of the United States. And it's time to begin considering urban sustainability options in coastal areas for a future that may be quite different from the past. It's time to begin charting out some contingency plans for discussion among managers, stakeholders, and policymakers in order to make it easier to move toward adaptive decisions if observed changes make that desirable. We need to start building a problem-solving social dynamic that helps us to work together as we increase our knowledge about what's happening. And we should start by identifying laws, rules, and practices that are obstacles to flexibility in urban and coastal governance and management in the future. Thank you.